Solar thermal energy is a form of energy and a technology for harnessing solar energy to generate thermal energy or electrical energy for use in industry and in the residential and commercial sectors. The first installation of solar thermal energy equipment occurred in the Sahara Desert approximately in 1910 when a steam engine was run on steam produced by sunlight. Because liquid fuel engines were developed and found more convenient, the Sahara project was abandoned, only to be revisited several decades later. Solar thermal collectors are classified by the United States Energy Information Administration as low, medium, or high-temperature collectors. Low-temperature collectors are flat plates generally used to heat swimming pools. Medium-temperature collectors are also usually flat plates but are used for heating water or air for residential and commercial use. High-temperature collectors concentrate sunlight using mirrors or lenses and are generally used for fulfilling heat requirements up to 300 deg C, 20 bar pressure in industries, and for electric power production. Two categories include concentrated solar thermal for fulfilling heat requirements in industries, and concentrated solar power when the heat collected is used for power generation. CST and CSP are not replaceable in terms of application. The 377 MW Ivanpah solar power facility is the largest solar power plant in the world, located in the Mojave Desert of California. Other large solar thermal plants include the SEGS installation, also in the Mojave, as well as the Sol Nova solar power station, the Andasol Solar Power Station, and Extresil Solar Power Station, all in Spain. Low-temperature solar heating and cooling systems. Systems for utilizing low-temperature solar thermal energy include means for heat collection, usually heat storage, either short-term or interseasonal, and distribution within a structure or a district heating network. In some cases more than one of these functions is inherent to a single feature of the system. Some systems are passive, others are active. Heating is the most obvious application, but solar cooling can be achieved for a building or district cooling network by using a heat-driven absorption or adsorption chiller. There is a productive coincidence that the greater the driving heat from insulation, the greater the cooling output. In 1878, August Muschau pioneered solar cooling by making ice using a solar steam engine attached to a refrigeration device. In the United States, heating, ventilation, and air conditioning systems account for over 25% of the energy used in commercial buildings and nearly half of the energy used in residential buildings. Solar heating, cooling, and ventilation technologies can be used to offset a portion of this energy. In Europe, since the mid-1990s, about 125 large solar thermal district heating plants have been constructed, each with over 500 square meters of solar collectors. The largest are about 10,000 square meters, with capacities of 7 MW. Thermal and solar heat costs around 4 eurocents kWh without subsidies. 40 of them have nominal capacities of 1 MW thermal or more. The Solar District Heating Programme has participation from 14 European nations in the European Commission, and is working toward technical and market development, and holds annual conferences. Low-temperature collectors. Glazed solar collectors are designed primarily for space heating. They recirculate building air through a solar air panel where the air is heated and then directed back into the building. These solar space heating systems require at least 2 penetrations into the building and only perform when the air in the solar collector is warmer than the building room temperature. Most glazed collectors are used in the residential sector. Unglazed solar collectors are primarily used to preheat make-up ventilation air in commercial, industrial and institutional buildings with a high ventilation load. They turn building walls or sections of walls into low-cost, high-performance, unglazed solar collectors, also called transpired solar panels. They employ a painted perforated metal solar heat absorber that also serves as the exterior wall surface of the building. Heat conducts from the absorber surface to the thermal boundary layer of air 1 mm thick on the outside of the absorber and to air that passes behind the absorber. The boundary layer of air is drawn into a nearby perforation before the heat can escape by convection to the outside air. The heated air is then drawn from behind the absorber plate into the building's ventilation system. A trombe wall is a passive solar heating and ventilation system consisting of an air channel sandwiched between a window and a sun-facing thermal mass. During the ventilation cycle, sunlight stores heat in the thermal mass and warms the air channel, causing circulation through vents at the top and bottom of the wall. During the heating cycle, the trombe wall radiates stored heat. Solar roof ponds are unique solar heating and cooling systems developed by Harold Hay in the 1960s. A basic system consists of a roof-mounted water bladder with a movable insulating cover. This system can control heat exchange between interior and exterior environments by covering and uncovering the bladder between night and day. When heating is a concern, the bladder is uncovered during the day, allowing sunlight to warm the water bladder and store heat for evening use. When cooling is a concern, the covered bladder draws heat from the building's interior during the day and is uncovered at night to radiate heat to the cooler atmosphere. The Skytherm house in Atascadero, California uses a prototype roof pond for heating and cooling. Solar space heating with solar air heat collectors is more popular in the USA and Canada than heating with solar liquid collectors, since most buildings already have a ventilation system for heating and cooling. The two main types of solar air panels are glazed and unglazed. Of the 21 million square feet of solar thermal collectors produced in the United States in 2007, 16 million square feet were of the low-temperature variety. Low-temperature collectors are generally installed to heat swimming pools, although they can also be used for space heating. Collectors can use air or water as the medium to transfer the heat to their destination. Heat storage in low-temperature solar thermal systems. Interseasonal storage. Solar heat can be effectively stored between opposing seasons. Aquifers, underground geological strata, large specially constructed pits, and large tanks that are insulated and covered with earth. Short-term storage. Thermal mass materials store solar energy during the day and release this energy during cooler periods. Common thermal mass materials include stone, concrete, and water. The proportion and placement of thermal mass should consider several factors such as climate, daylighting, and shading conditions. When properly incorporated, thermal mass can passively maintain comfortable temperatures while reducing energy consumption. Solar-driven cooling worldwide. By 2011, there were about 750 cooling systems with solar-driven heat pumps, and annual market growth was 40 to 70% over the prior 7 years. It is a niche market because the economics are challenging, with the annual number of cooling hours a limiting factor, respectively. The annual cooling hours are roughly 1,000 in the Mediterranean, 2,500 in Southeast Asia, and only 50 to 200 in Central Europe. However, system construction costs dropped about 50% between 2007 and 2011. The International Energy Agency Solar Heating and Cooling Program task groups working on further development of the technologies involved. The International Energy Agency Solar Heating and Cooling Program task groups working on further development of the technologies involved. Solar heat-driven ventilation. A solar chimney is a passive solar ventilation system composed of a hollow thermal mass connecting the interior and exterior of a building. As the chimney warms, the air inside is heated, causing an updraft that pulls air through the building. These systems have been in use since Roman times and remain common in the Middle East. Process heat. Solar process heating systems are designed to provide large quantities of hot water or space heating for non-residential buildings. Evaporation ponds are shallow ponds that concentrate dissolved solids through evaporation. The use of evaporation ponds to obtain salt from seawater is one of the oldest applications of solar energy. Modern uses include concentrating brine solutions used in leach mining and removing dissolved solids from waste streams. Altogether, evaporation ponds represent one of the largest commercial applications of solar energy in use today. Unglazed transpired collectors are perforated sun-facing walls used for preheating ventilation air. UTCs can raise the incoming air temperature up to 22 degrees Celsius and deliver outlet temperatures of 45 to 60 degrees Celsius. The short payback period of transpired collectors make them a more cost-effective alternative to glazed collection systems. As of 2009, over 1,500 systems with a combined collector area of 300,000 square meters had been installed worldwide. Representatives include an 860 square meters collector in Costa Rica used for drying coffee beans and a 1,300 square meters collector in Coimbatore, India used for drying marigolds. A food processing facility in Modesto, California uses parabolic troughs to produce steam used in the manufacturing process. The 5,000 square meters collector area is expected to provide 15 terajoules per year. Medium temperature collectors. In the United States, a typical system costs $4,000, $6,000 retail, and 30% of the system qualifies for a federal tax credit plus additional state credit exists in about half of the states. Labor for a simple open-loop system in southern climates can take 3 to 5 hours for the installation and 4 to 6 hours in northern areas. Northern system require more collector area and more complex plumbing to protect the collector from freezing. With this incentive, the payback time for a typical household is 4 to 9 years, depending on the state. Similar subsidies exist in parts of Europe. A crew of 1 solar plumber and 2 assistants with minimal training can install a system per day. Thermosiphon installation have negligible maintenance costs and in the U.S. reduces a household's operating costs by $6 per person per month. Solar water heating can reduce CO2 emissions of a family of 4 by 1 ton-year or 3 ton-year. Medium temperature installations can use any of several designs. Common designs are pressurized glycol, drain-back, batch systems and new low-pressure freeze-tolerant systems using polymer pipes containing water with photovoltaic pumping. European and international standards are being reviewed to accommodate innovations in design and operation of medium-temperature collectors. Operational innovations include permanently wetted collector operation. This innovation reduces or even eliminates the occurrence of no-flow high-temperature stresses called stagnation, which would otherwise reduce the life expectancy of collectors. Solar drying. Solar thermal energy can be useful for drying wood for construction and wood fuels such as wood chips for combustion. Solar is also used for food products such as fruits, grains, and fish. Crop drying by solar means is environmentally friendly as well as cost-effective while improving the quality. The less money it takes to make a product, the less it can be sold for, pleasing both the buyers and the sellers. Technologies in solar drying include ultra-low-cost pumped transpired plate air collectors based on black fabrics. Solar thermal energy is helpful in the process of drying products such as wood chips and other forms of biomass by raising the temperature while allowing air to pass through and get rid of the moisture. Cooking. Solar cookers use sunlight for cooking, drying and pasteurization. Solar cooking offsets fuel costs, reduces demand for fuel or firewood, and improves air quality by reducing or removing a source of smoke. The simplest type of solar cooker is the box cooker, first built by Horace de Sousa in 1767. A basic box cooker consists of an insulated container with a transparent lid. These cookers can be used effectively with partially overcast skies and will typically reach temperatures of 50 to 100 degrees Celsius. Concentrating. Solar cookers use reflectors to concentrate solar energy onto a cooking container. The most common reflector geometries are flat plate, disc and parabolic trough type. These designs cook faster and at higher temperatures but require direct light to function properly. The solar kitchen in Auroville, India uses a unique concentrating technology known as the solar bowl. Contrary to conventional tracking reflector, fixed receiver systems, the solar bowl uses a fixed spherical reflector with a receiver which tracks the focus of light as the sun moves across the sky. The solar bowl's receiver reaches temperature of 150 degrees Celsius that is used to produce steam that helps cook 2,000 daily meals. Many other solar kitchens in India use another unique concentrating technology known as the Scheffler reflector. This technology was first developed by Wolfgang Scheffler in 1986. A Scheffler reflector is a parabolic dish that uses single-axis tracking to follow the sun's daily course. These reflectors have a flexible reflective surface that is able to change its curvature to adjust to seasonal variations in the incident angle of sunlight. Scheffler reflectors have the advantage of having a fixed focal point which improves the ease of cooking and are able to reach temperatures of 450 to 650 degrees Celsius. Built in 1999 by the Brahma Kumaris, the world's largest Scheffler reflector system in Abu Road, Rajasthan, India is capable of cooking up to 35,000 meals a day. By early 2008, over 2,000 large cookers of the Scheffler design had been built worldwide. Distillation. Solar stills can be used to make drinking water in areas where clean water is not common. Solar distillation is necessary in these situations to provide people with purified water. Solar energy heats up to the water in the still. The water then evaporates and condenses on the bottom of the covering glass.